See the characteristic of filters. So this is the basic concept for designing any type of filter. So better to understand this first before proceeding for the designing of various filters, and also uh, just understand them, right? So a filter transmits or passes desired range of frequencies without loss and attenuates all undesired frequencies. So from the concept of image impedances, image transfer constant and all those things, we got attenuation constant through propagation constant, that is gamma. So that is, propagation constant is a complex number where real part is alpha and imaginary part is beta, and here alpha is attenuation constant and beta is phase constant. So since even here in the filters we got the attenuation term, we just need to proceed with the propagation constant only for the process of designing filters. Okay, fine. Now we have the relationship of sin h gamma 2, which is equal to square root of z1 by 4 z2. And listen here, z1 and z2 are given in bold manner, that means it is phasor, right? That means it is z1 bar by 4 z2 bar. But what is this z1 and z2? Okay, so here this z1 and z2 are series impedance and shunt impedance of the filter circuit. So let me show the example here. So here if you consider a pi network, here z1 is series impedance and z2 is the um, half of the shunt component, each shunt component. Fine. Similarly, if you see the T network, so here T network, if you see here, z1 is 2 times that of series component of the T network and z2 is the shunt component of the T network. So these kind of circuits we have already seen while discussing the attenuation concept, right? Okay, just you consider them like that. Okay, so what we are seeing, sin h gamma 2 is given with this, and you just substitute gamma is equal to alpha plus j beta, then it can be written like this. It is a trigonometric formula, that is hyperbolic trigonometric formula, and which is equal to square root of z1 by 4 z2. Fine. Now depending upon the type of z1 and z2, there are two cases. That means what? Type of z1 and z2 means what? Here the z1 and z2 are going to be either inductor or capacitor. We are not going to use resistor in case of filter design. Fine. So right, we are going to consider either capacitor or inductor. So the type of z1 and z2 means there are two different types, because the capacitive reactance is different, inductive reactance is different. So based on these we have two different cases. Let us see what are these two cases. Listen, very important, these things are, these two cases are the basic concepts for designing all the filters, right? So let us see the case 1. So if z1 bar and z2 bar are same type of reactances, that means if both are of capacitive or both are of inductive, then z1 by 4 z2 and sin h gamma by 2 are going to be real. Yes, because j and j will be cancelled if they are inductor. Similarly, if it is a capacitor, minus j and minus j will be cancelled out. Then there won't be any imaginary component and you will get only real. That means the sin h gamma by 2 is going to be real. Okay, this is one case. Okay, this is one case. Now, okay, when that is real, that means from this equation you will not be having any imaginary component, right? Imaginary component will be 0 and you will have only real component, which is nothing but square root of z1 by 4 z2. Fine. So that is given here. First imaginary component is equated to 0. So for that particular condition, it will be sine beta by 2 equals to 0, because the hyperbolic of cosine cannot be 0 at any time. You check this. Fine. So when that cannot be 0, but this product to be equal to 0, only sine beta by 2 must be 0, right? Then when it is 0, what it means, cos beta by 2 is equal to 1, because when sine beta by 2 is equal to 0, cos beta by 2 will be 1. Then sine h alpha by 2 will be equal to square root of z1 by 4 z2, right? Because I'm substituting cos beta by 2 equal to 1 in this, right? When you use that, sin h alpha by 2 will be equal to square root of z1 by 4 z2. With that you will get alpha is equal to 2 sin h inverse of square root of square root of z1 by 4 z2. This is the important formula which is equated to attenuation alpha. Fine, right. Now there is another case when Z1 bar and Z2 bar of opposite type. That means if Z1 is capacitive reactance and Z2 is inductive reactance, then what will be the case? In that particular case, we will get Z1 by 4 Z2 is negative. Okay, you just substitute and get it. Okay. And it is easy. When Z1 is inductive, it will be j omega L, and when Z2 is capacitive, it will be minus j by omega c. That means you are getting negative value, even though j and j is getting cancelled, but you will get negative value. That means Z1 by 4 Z2 is less than 0. Okay, then square root of Z1 by 4 Z2 will be purely imaginary, because square root of minus 1 will be j. Accordingly you will get imaginary part. So when you substitute these things, then real part will be equal to 0. That means sin h alpha by 2 cos beta by 2 is equal to 0, because there will be only imaginary part. With that, this will be equal to this, and then j will be cancelled. You will get this in the end. Okay, right. So the two conditions of operation of the filter with respect to the pass band and stop band are mathematically obtained from these equations. Okay, both these above equations must be satisfied simultaneously by alpha and beta. Okay, fine, right. In that particular case, two conditions are going to be occurring. Let us see what are they. Okay, first of all, we have considered in case 1 Z1 and Z2 are of same type of reactances, and in case 2 we have considered Z1 and Z2 are opposite type of reactances. Fine. So now let us see how to proceed further. Okay, now if you see here, there is some attenuation. Okay, fine. So sin h alpha by 2 equals to 0, right? When sin h alpha by 2 is equal to 0 from the case 2, that is alpha must be equal to 0 when beta not equals to 0. Okay, why here alpha is equal to 0 when beta not equals to 0? This is because since these two things have to be satisfied together, when cos beta by 2 is equal to 1, okay, then only we are getting this condition. That means when this is 1, we will get only sin h alpha by 2 equals to 0. Sorry, both the equation that should be satisfied are these two. Okay, so this is the 1 and this is the 2. So these sorry, not this one. So it is this one. This is the first one that should be satisfied in case 2. Along with that we should have the second one, that is this one. So when sine h alpha by 2 is equal to 0, right, we cannot have this okay. So first we will consider from the condition or equation 1, first we will consider sine h alpha by 2 equals to 0 case. Then in another case we will consider cos beta by 2 is equal to 0. Let us see what we are going to get the concluding points with those things. So the first case, that means in case 2, this is the first case. Okay, so for this case, since this is of case 2, z1 by 4 z2 is negative and sine beta by 2 is real, right, and that is equal to sine beta by 2 will be equal to modulus of square root of z1 by 4 z2, because when sine h alpha by 2 is 0, we are having cos h alpha by 2 is equal to 1. So when you use that here, you will get sine beta by 2 is equal to square root of z1 by 4 z2, right? Okay, now this signifying the region of zero attenuation. Zero attenuation is nothing but pass band, which is limited by the upper limit of sine terms, because this sine beta by 2 is nothing but this value, and this is limited by sine which is having upper limit of 1. So since sine beta by 2 is equal to 1 upper limit, this value of square z1 by 4 z2 must be between 0 and minus 1, because its value is negative, z1 by 4 z2 value is negative, so that's why we are considering it till minus 1, not plus 1, right? Okay, now the phase angle in the pass band is going to be given by the expression beta by 2 is equal to sine inverse of modulus of square root of z1 by 4 z2, right? So this modulus is indicating the positive value. Okay, now here with this beta will be equal to 2 sine inverse of modulus of square root of z1 by 4 z2. Okay, so this is the beta value, that is phase constant, when attenuation alpha is 0. Since this attenuation is 0, we are considering this case as pass band. Very important this is, you better understand this for understanding the further classes. Okay, so this is the case of sine h alpha by 2 equals to 0. Then in case 2, for making this one satisfied, we have another case, that is cos beta by 2 equals to 0. Let us see what we get in that particular case. So when cos beta by 2 equals to 0, we have sine beta by 2 which can be equal to plus or minus 1, and since z1 by 4 z2 is negative and cos h alpha by 2 is real from the above equation, so cos h alpha by 2 will be equal to modulus of square root of z1 by z2. Fine. Sorry, there is a mistake, it should be 4z2, it is square root of z1 by 4z2. So this is going to be signifying a stop band, because there is no attenuation, because attenuation is having some value which is equal to 2 cos h inverse of square root of z1 by 4z2 with this particular case. So this is the region of pass band, sorry, stop band, because there is some attenuation. That means attenuation is not equals to 0. When attenuation is 0, we'll consider it as pass band. When attenuation is not 0, that means there is some attenuation, so it is going to be considered as stop band, right? These are two important points, and listen carefully. These cases are getting arised with the case 2, that is when z1 and z2 bar are of opposite type of reactances. So this is the concluding statement here. So we are going to get stop band and pass band resulting when z1 and z2 are of opposite type of reactances. That's why we choose them as inductor and capacitors in the filter designing circuits. Okay, this is the concluding remark about this characteristic of filters concept. Fine, I hope you have understood this. Fine, next we will see what is meant by constant K low pass filter. First of all, what is meant by constant K filter, then we will see the different possible filters in that particular case. And listen, for all those filter types, this pass band and stop band conditions are important. We are going to do and also design all the filters based on these two conditions of zero attenuation, that is pass band, and non-zero attenuation, that means stop band. Fine, that's it.